As we begin graphing polynomial functions, that's a misnomer because we've actually been graphing polynomial functions all along. We have graphed linear, quadratic, cubic. As we start talking, and we'll talk about this fourth degree. And what I've done is I've given you some examples. Of course, a linear function is y to the x to the first power. Quadratics is y equals x squared. Cubic would be then to the x to the third power. A polynomial to the fourth degree, which would be y equals x to the fourth power, and then the fifth degree, and so on and so forth, would just be changing my exponent. So the general appearance of these functions, if you remember, we have a straight line when it comes to graphing a linear function. A quadratic function, we have generally this shape, right? The parabola. When we have a cubic function, it's going to come up and then it's going to make some kind of general shape like that. And then the fourth degree, we have what would be a W forming, or two parabolas. And then the fifth degree, we have that original third degree function, and then we're going to come up and have a additional. So if you'll notice, there's some kind of pattern. We start to have potentially, in quadratics, we have one possible term. In cubics, we have two possible terms, which is one less than that, and these are the maximums. In fourth degrees, we have three possible terms of the function. And so just doing that would be just some of the characteristics. Now, behavior, in behavior, so you'll notice as we talk about the quadratic equation here, in behavior is what is happening. What is happening to the end of my function as it continues on? And just to explain, I'm going to go into in behavior a little bit later, but looking at these functions and how would they change. So these are the parent functions, and the coefficient is positive because there's technically, ones out here. So these are the positive functions. And I hope that you remember when dealing with transformations of functions, when the a value is negative, it's going to end up it's going to be reflecting. So we're going to go the other direction. So my parabola now opens downward, and my direction has changed on these functions because they're now reflected. Just by that one characteristic. But looking at these, and if I look at as if I graph a quadratic equation, and I just take the parent function of the quadratic equation, it looks something like that, and that is y equals x squared, the end behavior. And we want to talk about that, and we see that this is going on forever in that direction. And so as my numbers approach negative infinity, positive infinity, negative infinity. Okay, so as my axes go that way, just a quick snapshot here. And so as we talk about that in behavior, if you notice, as we're following along this function, and it goes up like this, so as x approaches negative infinity, right? So as we go this direction, my y is going to approach positive infinity, because as my x gets greater negative, my y gets greater positive. And then as my x approaches positive infinity, my y approaches positive infinity, and that's what they're talking about in behavior. So that's what they mean. What is the end relationship of the function? Where is that stinking arrow going? And if I look at another example here, and I'll just take one of the cubic functions here, and let's see, not a very exciting cubic function, but that one is going to be y equals negative x cubed. because it is going to be flipped, and I look at it, and right here as my x, as x approaches negative infinity, my y is approaching positive infinity. And over here, as x approaches infinity, as it gets larger going this direction, it looks like my y value is approaching negative infinity. And that's what they're talking about when they talk about end behavior. What is the end behavior of a function? Where is it going in what direction? So that is one of those things that you should just be able to visualize, and understanding that vocabulary word and functions and looking at it and saying, oh, well, look at my number line. That's what's going on here. So as a quick reference, this function right here, just to look at it, as y approaches either as x approaches positive infinity or negative infinity, y approaches positive infinity. Okay, as this function, as x approaches negative infinity, my y approaches negative infinity. As x approaches positive infinity, my y approaches positive infinity, because that's the direction that it is going on the coordinate plane, right? If we just put a coordinate plane on there, we can see what's happening with the direction of the function. So looking at that, and so there we talk about our end behavior. And so as I work with sketching a polynomial, just sketching a graph, a general graph from its characteristics, and I'm given this example of x cubed minus 2x squared minus 8x. And just looking at this again, looking at my leading term, my degree is going to be to the third degree. So this is going to be cubic. So I should know that this is cubic. And when I go to graph it, I should know that its general shape, since a is a positive 1, its general shape is going to look like this. So my end behavior I should be able to identify just by that first term. And so I can say that, and I'll just go ahead and remove that. But let's see here. So I don't know any of my zeros yet, but I can find those by factoring. Remember, when we factor a polynomial, we can find its zeros. So I have x cubed minus 3x squared minus 8x, and they all have a common factor of x. So I can factor out x, and that leaves behind x squared minus 2x minus 8, and then I can go ahead and factor that. Remember, factoring a polynomial, a quadratic equation, is a fundamental skill acquired in algebra. So xx, I'm going to have possibly a negative 4 and a positive 2. That seems right. So using my zero product property to find my roots, I have x is equal to 0, I have x minus 4 is equal to 0, and I have x plus 2 is equal to 0. So x again is equal to 0. That's one of my roots. I'm going to use my inverse operations, and x is going to be equal to 4. That is another one of my roots. And then inverse operations, and x is equal to negative 2. That is another one of my roots right here, again using the zero product property. So as I go to graph this function, I can go ahead and identify my roots on the x-axis, x, y axis. So one of my roots is going to be 0. Another root is going to be 4. And another root is going to be negative 2. Okay? Now again, looking at my end behavior, right? So if I just draw a quick line through this function, this little diagram, that's going to be what my function looks like, because I have 1 root, 2 roots, 3 roots. So I know that the general shape of this is going to be, my end behavior is going to do that and that. So in this case, I'm looking at, I don't know what my y values are going to be, but I know that the general shape is going to look like that. I'm able to graph that just by plugging in my roots and knowing my end behavior. So that is sketching my graph. And in this case, we'll talk about some multiplicity coming up, but each one of my roots only appeared one time. So as we look at graphing again, now this function has already been factored for us. And it looks like when we go to do some, we know it's factored, so we have x minus 3 squared times x plus 2 squared times x minus 1. Well, when we go to use our zero product property, we're going to have x minus 3 equals to 0, and x plus 2 equals 0, and then x minus 1 equals 0. So we are going to have, again, our inverse operations. So x is going to be equal to 3, x is going to be equal to negative 2, and then x is going to be equal to 1. And looking at my exponents here, I know that x minus 3, it occurs twice, and x plus 2 occurs twice, and then x minus 1 occurs only one time. So this one is actually going to be the multiplicity, right? How many more times does it happen? Multiplicity here is going to be 2, 2, and just 1. So when we go to graph it, some of the things that we know when we graph it, because of multiplicity, we have even and we have odd. And that is going to dictate what happens to our function. My odd multiplicity, it crosses the x-axis, okay? And then my even function touches. It just touches the x-axis. And what do I know about that? Well, let's see if I graph this. Let's think about what is the degree of this function. The degree of this function is going to be 2, 3, 4, 5. So this is a fifth degree function, so it's going to look something like fifth degree function. Its shape is going to be this. And I know that it's going to be, my a is positive because all of these values right here are positive. I don't see any negative numbers in there. So my a, when I multiply it all out, my leading coefficient is going to be positive. So that's how I know that the direction of my fifth degree. So this would be 1, this would be 2 degrees, 3 degrees, 4 degrees, and 5 degrees. So when we go to graph that, I've already said that my roots are x equals 3, negative 2, and 1. So here's 1. Let's see here, negative 2 and 1. Okay, so they're all on there. Here's my y, here's my x. Don't know what my y values are going to be yet, but there they are. And it said that when I have multiplicity, right, of odd multiplicity, so we have an odd multiplicity, the x equals 1 only occurs one time. So that means it's going to cross over. It's going to cross that. So it's going to cross at 1. And it's going to do something at 3. It's only going to approach it. So it touches, and it touches at negative 2. So if I were to graph this, let's see, we know that the function crosses here at 1, and I know that it touches at 2 because my end behavior should be doing this and this. So if I touch, right, if I look this way and I'm going to work this way on my function, as I come up and I'm going to touch negative 2 because it's even multiplicity. And then I'm going to turn away from it. And then I'm going to go back and I'm going to cross over at 1 because it's odd multiplicity. And then I'm going to approach 3 again because it's even, and then turn back around. And then that should be the general shape of this function. Because here, even multiplicity, we touched the x-axis. It just went up. It went up and touched the x-axis and came back. And then as we approached the root of 1, it passes through that root because multiplicity is 1. and then we come back and we approach 3 again, but we don't cross over the x-axis because it's multiplicity of 2, and we continue going up. Again, takes a little bit of practice, but you know, multiplicity is one of those things that will help us graph. What is the rule for multiplicity? If a root is a multiplicity even number, even value, then it touches the x-axis, it does not cross. And then if it is an odd multiplicity, it crosses the x-axis. Okay, so at what root does the graph of this function, f of x equals x plus 4 to the 6th power times x plus 7 to the 5th power cross the x-axis? Well, the multiplicity of this root is 6. The multiplicity of this root is going to be 5, so this is even multiplicity. This is odd multiplicity. So we said that when it's odd, odd crosses the x-axis, and when it is even, it touches the x-axis. It doesn't cross the x-axis. So at what root does this graph cross the x-axis? Hopefully we know that, well, if we took x plus 7 and made it equal to 0, did our inverse operations, the root where it crosses over the x-axis is going to be x equals -7. And if I wanted to graph that, well, goodness, I know that there's 11 of them. 11, which means it's odd, which means it's going to do something like that in the long run. I have 2 roots, and at -7 it's going to cross. At -7 it's going to touch at -4. So it probably does something along the lines of this, this, this. And that's what it looks like if I were to put it in the calculator, just looking at its general identification. Because this was the even multiplicity where it only touched the axis. This was the one where it crossed over. So again, graphing polynomial functions, understanding their end behavior and what's going on, understanding the rules of multiplicity, whether it's even or odd, and examining the end behavior or the way the graphs turn based on their exponents and their degree. And if you think about it too, we just talked about multiplicity. This one right here, the example we used is x squared, which if we factored that, right, x is equal to 0. And so since it's even multiplicity, we touch at 0, we don't cross. So with that, we're going to continue graphing polynomials, and it will become more familiar, and there's a lot of things that we can graph just identifying the characteristics.